Right, in this video, we add one more force to the situation. Let's review what were those main forces. It has a spring system, it has its own system and contraction and kind of contraction force that is described using this Hooke's law. And gravity is pulling it down, that's second source. And another one is action-reaction result, which is air drag or drag force of the medium in here. Those are the three forces. The key thing to observe in here, Hooke's law states that the forces created by spring is depending on its position, where the mass position is. And this one is constant. It does not depend on where thing is and how fast it's moving. The gravity is always constant. And air drag is depending on how fast it's moving. So it's about the dependence of y and dependence of y prime. It is this important observation you need to make. We want to add so-called external force. I'd like to describe the situation as if we have a machine and this is kind of reacting to magnetic force. So we have our machine out there, very close to the system. If we turn it on, it creates some sort of electric magnetic force, so it affects its motion. So the key thing is that creation of this force is not really detecting where this one is and how fast it's moving. It's just our own algorithm and creates it. So this is purely our algorithm phi t. And it does not depend on where the machine is, where the mass is and how fast it's moving. So it's purely our algorithm depending only on time. After 3 seconds, this machine generates this much of the force. After 5 seconds, this generates this much of the force, and so on. But we can create a machine that detects where it is and how fast it's moving, and then react to that. So it's possible, but right now, our description of external force has nothing to do with not detecting where it is and how fast it's moving. It's just, apply this own algorithm, only depending on time. So this was the general picture without the external force. There's a Hooke's law, spring force created by spring system and gravity and drag force there. What we have to do now here is we have to add this external force generated by the machine. If you turn that thing on, and it's going to start moving in here. So in our formula, it was like this before. Now we have additional term, and here is phi of t right there. Good. And as we divide everything by m, we have phi of t scaled by this m, and we have here a 1 over m phi of t. It does not have y or yt in it, y prime in it, so we keep it in the right-hand side. All right. So it did not affect this operator, so therefore our L remains the same. So the classification of the shape of the result is pretty much the same, and it's that when we come up with a particular solution f0 of, let me change the color, f0 of being not just g, but we have to figure out what could be the particular solution that takes care of this external force as well. So this, depending on what this phi t is, it could get really complicated. So that's we have to look at some simple example to understand. So I consider this simplified situation. Suppose this information, the mass and all the spring constants is given, and you try to write the equation into this form, and you may arrive at it here like this. So it looks a lot like that. Suppose it's 9 over a over m and k over m. They all calculated, and it became 9 and 14 and being positive and positive there. And g is the gravitational constant, and this whole thing, 1 over m times phi t is worked out as like this. So, m is a constant, so therefore you can see that phi t really has this sine t in it, and whatever the constant is. So the nature of this external force, phi t, was vibration. That's definitely vibration in here. So if you turn this machine on, it generates this type of vibrating force. constantly and changing as a force. So if you put that force in there, how is it going to affect the motion of the spring system? That's our problem there. So it's going to be solved in this way. First of all, we write down this linear operator there, L, and this y is what we're looking for, and we have this g and 1/2 times sine t. This is the solution that we're looking for. So that we were looking for f0, the particular solution that hits this one, and then we can quickly calculate the kernel of this operator, and that's it. Because it's separated like this by sum nicely, we can work this one like this. First we calculate what goes to g and what will reach is 1/2 times the sine t. If you look at this two separate problem, using the linearity of this operator, we can add this together, and the right hand side is going to be this one. If you think about what this is exactly the problem without external force. Therefore we know the answer is mg over k there. So mg over k, if you go through, then you definitely get this one here. In this case, I think it's just simply g over 14, that you can easily see that. So instead of writing it abstractly like this, let's write it down as a g over 14, write it that, g over 14, that gives you g, and derivative 0. So that's one part of the solution. The other part you have to think about, this is something that we recently must have practiced, so it goes like this. What could be the, I'm just going to continue in here. To attack that part, we have to consider this is a linear, and then you can see this has whether it has a complex solution or real solution, and then like sine t is the kernel. If the sine t is the kernel, it should have been like y double prime plus y. So that sine t is definitely not in the kernel of this operator here. So definitely trying a times sine t plus b times cosine t is going to definitely reach this one. So you will have a prime sine t and b prime cosine t is going to show up, and these a prime and b prime are in terms of a and b in linear form. So if you set up linear equation of 2 by 2 matrix and so on, you can solve it. So we're going to skip that computational part and give you an answer. It turns out, and this a and b are the following numbers. Right, forgot to say one thing that I can say easily. This one is supposed to be 1/2 here, right? A prime is supposed to be 1/2, so that it matches the right hand side, and b prime here it's supposed to be 0, and that's the equation that you're supposed to solve in terms of a and b. And once you do that, turns out these are the coefficient that reaches exactly 1/2 times sine t there. So we know what reaches 1/2 times sine t, and g over 14 will reach the 14 g there. So altogether, we can conclude now easily that particular solution that we're looking for, let me erase that, particular solution that we're looking for is this one plus that. And this one, the operator, so I think, let me write down f0 here. f0 is g over 14, that's one part. And this is another part, 13 over 500, and rest of the part is written here. So let's look at the kernel. What is the homogeneous solutions equation of a homogeneous equation there? That part has d squared plus 9d plus 14i, so that is d plus 2 and d plus 7, I think, right? I forgot i's in there, so write down that I. Good. So the kernel is e to the negative 2t and e to the negative 7t. So general solution yt must be c1 of that e to the negative 2t, c2 of e to the negative 7t, and there is this particular solution of that shape. So it's a g over 14 plus 13 over 500 sine t. It's like that. That's the solution here. Think about this is different from the example that we looked at in an earlier video. So let's think about the motion in here. This part dies out quickly. Let me write it over here. This part dies out quickly. Maybe it has a slight one bump in there, but this part definitely an oscillating vector. That's understandable because this external force is creating constant vibration, and there's this overly damped situation, So what is coming from spring constant, forces from spring system and air drag is so strong it dies out everything. So only force that is really come into effect at the end of the time period is this oscillating effect right there. And it's interesting that it is not just the sine t that survives, and there is this more complicated shape shows up. And although it dies out at the end of the time period, still it is not just the sine t, it is dealing with this slightly different shifted phenomenon. The magnitude is slightly different as well. I think that part's interesting. Well, one way to explain is its momentum, is the initial velocity and things like that. Suppose, and let me interpret it this way. At the end of the day, and forget about what happened before, let's say that was a time period t equals, let's say, 20 seconds later. What is coming from the spring system is almost none. It is almost zero, or a very, very small amount of force from spring system, and because the velocity is small, the drag that it's dealing with from this force is relatively small. So it is really about the force coming from the external source and the drag force that's coming out of that. It is mainly that. I think so. Whatever the position, for example, and this initial velocity, the position y and initial velocity, and that's the initial momentum we have it in there, and what this external force, sine t basically, with some constant proportionality, is doing, that is pretty much the governing the rest of the pod. But we can't completely neglect that forces coming from the spring. I think that those are determining the behavior at the end. So it is tempting that, okay, at the end, if it's overly damping, that the force that survives is just external force, and the behavior at the end of the time period must be just sine t type of behavior. But it's a little bit shifted because of the cosine, and magnitude is slightly different. But at least we keep this period and frequency phenomenon that is governed by the external force. That kind of makes sense here. So let me show you that how this function looked like, and that's the exponential part. And by initial condition, only the C1 and C2 are changing. And if we change the initial condition, and this part is not changing at all, only this part, the kernel part, is affected. So that's the situation. So I'm going to change this values a little bit, and here's how it looked like. First of all, and this part is the picture in between the 0 to 3 seconds, and this part is a little later, 3 seconds to 14-second period. The beginning, as you can see, we have, because it's not so small at the beginning in here, that exponential part, it kicks in and do this much at the very, so if C is C1 is small and C2, let's say C1 is very small, and you can see at the beginning we have this oscillation. And I set this equilibrium position to 0 in here. If you change the C2, and you can see that phenomenon we observed earlier in the video with overdamping phenomenon here. What happens to the tail part is it zoomed in, you can see the scale is a bit different. And if you look at that part, this overdamped part, or it is not affecting very much. It's only this oscillation part from external force is coming into effect. If I change the C1 and C2, doesn't matter, this guy just stays in, because if you look at this formula, there's no C1, C2, the initial condition doesn't affect this external force in there. So that's the behavior of the motion. At the beginning, we have this overdamped phenomenon and relatively very small external forces appearing at the end as it damped out. So that's the situation. Thanks. Let me consider another important example. This is always introduced in every standard text that seems like the same thing we're looking at, but this vibration we're adding, this external force is a slightly different. It's very subtle difference. It makes a big difference into your, for your solution. So it's a lot simpler in terms of the operation is involved in here. Seems like there's no air drag. We almost ignore that air drag in here. Maybe that's air drag. It's very, very small. But we do have the strong spring constant involved in here. So let's look at this case, and G is the gravitational force again, and this is external force divided by the mass part in here. It's like before, we have this part of the solution, and definitely G divided by 16. That part's easy. That's going to get you G there. So if you plug in G divided by 16, that picks up G there, and that's 0. So if you take care of that part, we have to figure out what this part is. That hits this 2 times the sine 4t, and we have to figure out what that answer of this one is. The problem is that if you look at this part in here, and this equation that's associated with that is a d squared plus 4i, that is 16i. 16i equals, so if you look at this one here, you can see the kernel is a sine 4t and cosine 4t, like that. So that's a problem, because if you try sine 14 there, it's going to be 0. So we practiced this before. In case this is the case, then you have to try the following trick. That the kernel, for that of the kernel, we have to try at plus b sine 4t. So if you just try sine 4t, and it's going to die because it's a kernel, but if you stick in at, when you go through the constant coefficient, the sine 4t survives, so there's a chance that we can figure out what this a and b that does it. So, but when you do that, we usually have, if it has a linear term, we usually have cosine kicks in. But as you can see, that when you do the sine 4t, there's no cosine kicking in. Differentiate 2 times, that's going to be, I was wrong. I think when you differentiate 2 times, because of the product rule, you do have a cosine 4t kicks in, so you have to be careful. So let's write down the full version as a cosine 4t here. So if you try this one, definitely you will have sine 4t coming out. What you have a whole lot of other terms coming out in here as well. But by setting this one equal to sine 4t and all the other coefficients of t times sine 4t, cosine 4t, t times cosine 4t, and all that will be 0, because this is the only thing we want. So that's going to be a 4x4 system of equations, and out of that we discover the following solution. Right, suppose we did that 4x4 system, and turns out this is it, and this is going to be a is 0 and b is 0, turns out, and c is negative 1/4, and d is 0, and if you do that, you get this positive 2 times sine 4t. Like we did it earlier, the particular solution for this whole thing is that this constant term plus the one that we have it here. And this is fairly easy. We have it already written down. Then sine 4t and cosine 4t is going to be the kernel, so we can write down, and over here, the general solution y is going to be c1. Let's write down cosine first, cosine 4t plus c2 sine 4t, that's the kernel part, and particular solution we have here is a g over 16 plus or minus what we have over here. It's negative 1/4 t times the cosine 4t. All right, the spring mass system with no air drag involved, only the spring system is the main force plus the gravity, creates this much of a nice pure oscillation. But the external force that happened to be exactly the same resonance, same frequency we added in here, that's the difference. That's the difference from the early example. Then this is the additional part it kicks in. Before we look at actually the graph of this function using the computer software, we can easily say that this t is going to be a problem, as you can see here. And cosine t oscillates back and forth, but t is going to amplify this one. And then this yt is going to be, well, that part is just about this one right here, but this part here will create eventually going in a bigger and bigger motion like this. So according to this description, if you kind of generate using this machine, the electromagnetic force, external force, that has same frequency of a spring system, and then eventually it's going to amplify the motion to and wider. And I've read this following incident that the bridge, if you think about a bridge here, let me draw a picture, bridge, and under it there's water passing by, there's a bridge, and these are the kind of legs that's supporting the bridge over here. The water is going by, and there's wind and everything, but water is usually the main source of creating little vibration to this bridge all the time. So you can measure there's some constant, relatively constant frequency and vibration is created. So if you set a little bit of maybe the wind happened to be affecting this bridge with exactly the same frequency in here. Suppose that happened for a certain period of time, that's 1 or 2 minutes, then it can increase the amplitude effect in here, and if it amplitudes increase, then maybe it's the beyond the ability the bridge can hold, and then it eventually breaks. So it's not requiring strong force of the wind, it is just the right frequency of this wind might break the bridge in here. So that's the mathematical description of something like that can happen. Forgot to mention the situation here, and this wind that I was talking about with the right frequency is the source of external force, and that kind of calculation might explain that kind of phenomenon. Strong wind for a long time can break the bridge with the right frequency in there. So this type of phenomenon is called a pure resonance, I think. There. That's an important example whenever this spring mass system is introduced, and this phenomenon in mathematical description is interesting. Thanks. Forgot to show the animation, the pictographs of these function in here. So that's the main oscillation part, and this is created by external force. So when I sketched it here, and this is only the beginning part, so you can see at the beginning part that t is very small, so this part doesn't come into play much. It's mostly dominated by usual spring system force that looks a lot like usual simple harmonic motion. These are again initial condition that doesn't change very much, but just a little bit of amplitude. It's depending on what the initial momentum was and stuff like that. That changed a little bit. But this is a period between a lot later time period, like 4 seconds to 30 some seconds, and you can see I even increase the magnitude to 10 to -10, as you can see as time goes. There is this force all the time there, but because of that t times cosine 4t, it increases this magnitude gradually, and that is coming from that factor in there. So I'm going to show a little bit and how this affects the final part. It's interesting, as you change the C1 part, it actually affects the behavior around that position a little bit. I think it is just the critical moment that it's kind of canceled and died out around that time period as we change the initial values. But eventually it picks up this amplitude again. Thanks.